Hello everyone, and thanks for attending my talk. First, I'd like to thank the GraphXD organizers for inviting me to speak. Today I'll be talking about NetworkX. For those who don't know, NetworkX is the Python reference library for network science algorithms. At a high level, it's a very flexible Python package. It allows you to have arbitrary edge data and node types. You're also able to read and convert to many different graph formats. And in addition to being able to write and read these formats, it's also interoperable with many other graph libraries and array libraries as well. It's easy to use. It's a pure Python library and inherently multi-platform. It's very readable code, which is one of its big selling points. A lot of people like to look at NetworkX code just to better understand algorithms and how they're implemented. It's well documented. So it includes references to the literature as well, and it's well tested. I also should mention that it has a very nice natural API. It's a very powerful package with hundreds of functions for creating, manipulating, measuring, studying, and visualizing networks. And it handles data sets of moderately large size with up to maybe 10 million nodes and something like 100 million edges. So for the outline, I'm going to be briefly mentioning a bit of its history, telling you a little bit about the data model, some of the features, some recent improvements, and finally I'll conclude with the invitation to contribute. So for history, almost 30 years ago, the very first public release of Python came out in 1991. The very first version of Python, from the very beginning, dictionaries were a first-class citizen, and you'll see dictionaries are a very important data structure for NetworkX. But Python didn't offer a graph data structure per se. However, in 1998, Guido van Rossum wrote a little essay called Implementing Graphs, where he proposed using dictionaries to implement graphs, and that's essentially at the very heart, still today, of NetworkX's graph data structure. NetworkX itself began around 2002 at Los Alamos, and it was really a research-driven project. And it interestingly started out, I believe, as research into the study of epidemiology or disease outbreaks and spread. However, Los Alamos, didn't immediately release that as public code or announce it to the larger community. However, after a couple years of development internally, it was first announced at the SciPy conference in 2004, and the first release of it came out in 2005. Just to give you some context, NumPy, the first public release of NumPy came out in 2006, although both numeric and numarray, the two precursors of NumPy, were already available at that point. But NetworkX has been in the ecosystem longer than NumPy itself. And then, shortly after the public release, a growing community of developers, largely from drawn from graduate students doing research as well as faculty members doing research, joined and became part of this developer community. The library grew fairly rapidly to become very large and useful for lots of purposes. And the 1.0 release came out in 2010. Then partly because of the Python 2 to Python 3 transition and some of the API changes that happened there, in 2017, NetworkX had a major interface redesign that was released as a 2.0. In the last year, NetworkX has received a grant from CZI's Essential Open Source Software for Science program, and that has allowed us to do some major cleanup and remove a lot of technical doubt, as well as improve our community infrastructure. We'll have a 3.0 release imminently, possibly by the end of the summer. We've done a lot of the original work, or most of the work is done on that. It's just going to be a matter of cleaning up a few things left over. But hopefully with the 3.0 release, we'll be in a really good shape for new core developers and contributors to come on board. And so I'm hoping some of you out there listening to this talk today will be encouraged and become interested in joining our community. And I'll talk more at the end about how that process would work. Okay, so onto the data model. So before we do that, I'm just going to give you a very simple example so we see some code and have an example to talk about. Up here in the right-hand corner, we've got a graph with 4 nodes, A, B, C, and D. It's a weighted, undirected graph, so there's an edge between A and B that has weight 4. And the way we would implement or make this graph in NetworkX is first we would import NetworkX as NX. You may be familiar with import NumPy as NP, so this is sort of the equivalent idea. And then we can create an empty, simple graph using NX graph and assign the variable g to it. And at this point, we can just go ahead and add the edges. So we add the AB edge with weight 4, the AC edge with weight 3, and so on. Now that we have this graph, NX has a bunch of algorithms, in particular, for example, shortest path. And so we can use NX to compute the shortest path in the graph G that we just constructed between nodes A and D. And we're going to look at the shortest weighted path. So if we didn't do the weighted path, either ABD or ACD would both be paths of length 2. But this is weighted, so we're going to sum up the weights on those edges. And then the ABD has 4 plus 2, so 6 versus 7. So the algorithm outputs A, B, and D. This is implemented by default by Dijkstra's algorithm. So there's other choices that you can specify if you want to specify the method when you call this shortest path. And if you've taken an introductory algorithms course, shortest path is probably something you encountered. It's a very classic algorithm and used in lots of contexts. You could imagine being useful for things like shortest distance or routing or any sort of optimization problem that you have on a graph. All right, so how do we represent this this dictionary we just created internally? And the way we do it essentially is a dictionary of dictionaries of dictionaries. So here we got a little representation of this, and you can see the graph structure, or the dictionary structure. So let's go in this internal dictionary. So dictionaries in Python are represented by brackets with comma separated tuples of colon delineated items. So this is just a dictionary with one key weight, and the value of that key is 4. So stepping back out, we can see the bigger dictionary has 4 keys, A, B, C, and D. So the keys of the dictionary for this graph are the nodes of the graph. And then the values of each of those nodes are essentially the adjacency list representation. So A is adjacent to B, and it's adjacent to C. And then the values of those adjacent nodes are the edge weights or edge attributes. So in this case, there's only one attribute on the edge, and it's weight. And this is an undirected graph, so the AB edge is represented both as B being adjacent to A, but also A being adjacent to B, so it's a little redundant there. Okay, so a little bit more high level. We've basically already said this, but just to reinforce it, a graph in NetworkX is just a dictionary of dictionaries. At the top level, it's a dictionary with nodes that are the keys of the graph, or the keys of the dictionary are the nodes of the graph. And so that means that the nodes can be any hashable Python object. Dictionaries are represented or implemented with a hash table in Python, so that's why we have to have it hashable. The edges themselves are tuples with optional edge data, and we also store that in a dictionary, including the optional edge data. And using these dictionaries gives us a couple things. So natural syntax. So G of U returns the dictionary of neighbors of U in the graph G. GUV returns the edge attribute dictionary of the edge UV. We're also able to do testing. NNG tells you true if the node N is in G and false otherwise. And also allows us to loop over all nodes in the graph. So for N in G. This is an efficient representation. So adjacency lists are really good for sparse graphs because it only stores edges that exist and not edges that don't. So if you use like a matrix representation of a graph, by default you have to put in zeros for all the missing edges. However, you could use a sparse matrix representation to deal with that. But with adjacency list, you get that directly. Then because of this data structure, finding in edges and removing edges are just require 2 dictionary lookups. Python dictionaries, as everyone knows, are very highly optimized since it's a very core data structure, and there's been a lot of work on making the dictionaries work very well in Python. Okay, so a little bit about the features, and if you go to the tutorial or attend the tutorial later today, this these features will be fleshed out in a lot more detail. So this is just a very high level version of this. So let's first start out with the types of graphs you can deal with. So the basic data structures, we already seen the simple graph. We also allow you to have directed graphs as well as multi-graphs, so graphs with parallel edges and self-loops. Because we use this dictionary representation, nodes can be any hashable Python object, so text, images, XML records, etc. And edges can hold arbitrary data. They don't even have to be hashable. So, ideally or classically, you might have weights or time series, but any kind of data that you need to attach to your edges is permissible as long as it's a Python object. Okay, so how do you get a graph? Well, you might have collected some data, and you might have a graph stored in some data format. And NetworkX provides many tools for reading different formats of graphs. You can also write to them, so you can both read in data that you've collected, but you can also, after you process it, save your graph and then read it into another program, graph analysis package for post-processing or subsequent processing. There's also a number of methods that are attached to these graphs. So first, these views, which if you're familiar with Python dictionary views, it's the same idea. And this is really where the focus of the 2.0 interface refactor was focused. So gnodes is a dynamic window onto the nodes of the graph. So if you had some variable and you assigned gnodes to it, then if you go and change the graph, that variable will automatically be updated. We can also query things like number of nodes, and this is not dynamic. This is a static kind of function. We can also modify. So we already saw you can add edges to the graph. You can add edges from some bunch of edges, or you can remove edges. You can also add and remove nodes as well. So we've seen now two methods for constructing graphs. One is you can do this hand construction version where you start with an empty graph and you add edges as you wish. Of course, to make really complicated graphs, you might want to do that programmatically, but even then, that may be not ideal. You can also have collected data, and that is in some kind of format that you can load into NetworkX. In addition, we have these generators. So classic graphs like the barbell graph, which is basically two complete graphs connected by a long path, and you can specify how many points you want in each, or how many nodes you want in the complete graph at the two ends, and you can also specify the length of the path in between the barbell complete clusters. And this would be useful for something like if you're interested in studying random walks. This is an extreme version of a graph where you wouldn't easily get from like one of the complete clusters to the other complete graph by just walking randomly, because it would be very difficult to walk from one cluster to another. You'll likely stay in one of the complete graphs. And if you start going across the long path in between the two complete graphs, you're likely to end up back where you started. Complete graphs, star graphs, many other of these classic graphs that if you're coming more from a graph theory or math background, you're likely to be very interested in. There's also random graphs, which are used much more in science, as well as math. So the Erdős-Renyi graph, where you sort of have the simplest type of random graph you can imagine. So you have n nodes, and each edge between any two pairs of nodes occurs independently with some probability p. These graphs are well studied. A lot of mathematical properties are known about them. For instance, they have very nice properties, or good properties for the average shortest path between any two pairs of nodes. It scales up as n goes large. That average number grows log n, which is one of the ideas behind what's called small world graphs that you may have heard of. Small world graphs have this small average path length between any two nodes, but they also have a large clustering coefficient, with the Erdős-Renyi graphs do not. So the Watt-Strogatz is a type of random graph that gives you both of those properties. We have other ones as well that give you better, more realistic, although typically there's some trade-off between the different models with how realistic they are on one aspect of a real-life world network versus another. Random deregular graphs is another thing we offer. And we also just have many, many other types of things like expanders, which are really nice, interesting classes of graphs, which are, basically very sparse graphs. So they have very, very few edges. But in many ways, they act as if they're dense graphs. So, in a dense graph, you can get from any, node to another node with just one step. In an expander, you can't do that because there's very, very few edges, but you can get very quickly from one to another. Another thing expanders have is that they really don't have any choke points, so you can't just knock out a small subset or maybe one or two nodes and disconnect the graph. There's other things like lattices, degree sequences, other types of social network generators we have, just many of these generators. Another thing you can do is, in addition to generating these graphs randomly or in a static way, or reading your graphs from data, or hand building them, you can do operations on graphs. So take a graph and produce a new graph from that graph or from a collection of graphs. So complement, subgraph. You can look at new types of graphs that are power graphs, unions, intersections of two different graphs, Cartesian products of two graphs. We also allow you to do things like union all with many graphs. So the algorithms, very similar, except some of the algorithms don't return back graphs. They might return back some number or some measure or property of the graph. Things like centrality, clustering, coloring, communities, on and on. I won't read this, but I'll just point out like link analysis, for example. PageRank is a classic link analysis where you're really trying to figure out properties of the nodes by just looking at how the nodes are connected with no other information. So PageRank is the algorithm that sort of got Google started for search engine. But anyhow, if you want to learn more about these, they're extensively documented in our online documentation, and you can also look up algorithms in textbooks and other places. I won't go into detail. In addition to this file I/O, we have the ability to convert, and partly this is because of NetworkX's role or position in the scientific Python ecosystem. So it's really at the same technique-specific level as scikit-learn, scikit-image, or pandas or stats models. Right on top of SciPy, matplotlib, but below a little bit of the domain-specific packages for a domain like astronomy or biology. NetworkX itself provides functionality for converting to and from dictionaries and lists, NumPy arrays, SciPy sparse matrices, pandas data frames. And because of its position in the ecosystem, many other packages also are aware of NetworkX and either allow you to represent its graphs or convert its graph format, data format to a NetworkX data format, or they use the NetworkX data format or data structure as their core data structure for some other higher level network analysis. And I've just listed a few here, but there's many more. NetworkX is really focused on algorithms. We're a reference library. However, we do support some basic drawing functionality using matplotlib. Here's just some examples of some drawings of graphs that we have in our gallery of examples, which I'll say a little bit more about later. And in the gallery examples, you can click on these and find the exact code that generated them. And it's often a useful way of, when I want to go draw a NetworkX graph, I typically go to the gallery and click around and find my way. Okay, so recent improvements. So I mentioned that we recently got a 1-year grant, and that really has allowed us to do some code and documentation improvements. We've improved some of the algorithms and our testing infrastructure over the last year. We removed a lot of legacy code, so there's a ton of newly deprecated functions that we'll be removing in 3.0, and the deprecations are coming out in the upcoming 2.6 release. We've also done some improvements to our documentation, so in particular we focused a lot on the gallery examples, so they're much better shape than they were about a year ago. And we've also just begun creating these notebook repositories. So it's a new repository. So our examples themselves are very small and toy examples, and these notebook repositories we're imagining much more large narrative exposition type discussions of network analysis, and I'll say a little bit more about that in a moment. But we had a lot of focus on community structure and process. So, NetworkX has been around since 2002, but we hadn't ever made a logo or had our own domain name, or we hadn't joined on Focus, and many things. And we've done all that now. So we've got our own logo. We've now own networkx.org. We joined NumFocus. We've also recently adopted a code of conduct and a mission and values, which are very useful. We've also spent a lot of time improving our contributor and core developer guides. We create a roadmap and an enhancement proposal process. So the enhancement proposals are ways of designing new large features. If you're familiar with the Python enhancement proposals or PEPs, or the NumPy enhancement proposals, NEPs, you'll have a sense of what we're talking about here. We've also formalized the governance and decision making, and officially developed a core developer team. We now meet weekly, and so the planning and community structure around NetworkX is much better than it was a year ago. And a lot of this stuff was done and put in place because we're hoping to recruit and grow a new generation of contributors and core developers. So really this was done for people like you. So hopefully some of you will come and look at these documents. All right, so here's the invitation to contribute. So most of this I will be showing you some stuff online, but just quickly, there's two main repositories that I think would really benefit from contributions from people like you. So the main one is our NetworkX package itself, and that's a GitHub NetworkX. We're looking for things like improved documentation, new features, new algorithms, better tests. We need help with code review for people submitting PRs, and bug fixes or performance enhancements, things like that. And then this NetworkX notebooks, which I mentioned, and we're just getting started there, but we're looking for two types of contributions mainly at this point. So one is a pedagogical notebook. So you can imagine, maybe you know some aspect of graph theory or network science, and you really would like to explain it to others. And you can write these Jupyter notebooks where you have a lot of text, math, figures, but you also can embed some NetworkX code. And so you can use NetworkX to help explain these concepts, and you can use these concepts to help explain, and document NetworkX. We're also looking for some real-world examples. So, because we run our gallery every time we submit a PR to make sure nothing breaks, a lot of those gallery examples are very small toy examples with toy data, and we'd like to see some, real-world data examples. So, if you're using NetworkX for your analysis and you have some real-world data, which I imagine many of you do, we would really be interested in seeing some nice presentations of how you analyze your data and what you've done. So maybe you've got a paper out where you use NetworkX for doing some analysis, but the paper itself doesn't include the code. You could have a supplement to that that we would love to have in our notebook repositories. All right, so let's take a look at our NetworkX repository. So this is what you'll see on NetworkX GitHub's site. So when you first come here, before you do a contribution, which you do through a pull request, it's good to first look through the issues to see if you can find a bug that someone's reported, or a request for a new feature, or maybe you have an idea yourself that you can create a new issue for, or a new bug report before you try to fix it. Because it could be that you're running a stable version of NetworkX where the bug exists, but it doesn't exist in the code base. So it's worth getting a little check before you try to spend too much time on that. We've also recently started using the GitHub discussions, and you can come here and have discussions about algorithms or ideas, or any other thing that you want to talk about in the NetworkX realm. And this is a good way to get started with ideas before you write too much code that may not necessarily make sense for the project. And so once you get a pull request, I'll talk a little bit more about how you can find out how to do this, but just to give a sense of what this looks like. Here's one here, and what happened was, there was an issue reported by some other person. This contributor felt like they could, address it, so they made a PR, and that PR begins this process where, the core developers will have a discussion with you. There'll be discussions about the API, the implementation, where things go, how they should be named, things like that. At the end of this process, we hope that there's a much better final code submission before we merge. There's also a number of checks run each time you submit or update your pull request. So we check that tests are run. We check that the style and formats, that you're abiding by our style and format. We also test on a bunch of different operating systems with different versions of Python and with different installed packages, using PyPy, some of our optional install packages, pre-releases of software we depend on. We also build the documentation to make sure that nothing broke there. All right, so how do you get one of these PRs started? The best thing to do, I think, is just go to our website, networkx.org. And if you're also a user, there's lots of information here. You can find the mailing list, You can also find information about the last stable release that you'd get if you did a pip install. But if you're interested in contributing, the place to go is to the documentation for the development code, just because this documentation stopped getting updated in August, and this is still getting updated daily. All right, so if you come here, you'll see a few things. So those would be information about how to install NetworkX, information, a little tutorial to get you started. So if you've not used NetworkX before, a tutorial is a great place to begin. There's a gallery, which I mentioned before. And so, here are some of the examples I was looking at. And, if you click on one of these, you'll see the exact code that is used to make it. You can also just copy and paste, or you can download the Python code or IPython notebook or Jupyter notebook. And like I said, this is something I find very useful constantly. There's also a reference guide, and finally, though, you'll be looking at this developer guide. So the very first thing you should look at is our code of conduct. We take it seriously, and we've never had any problems with it, and we hope we don't have any problems with it, but we will take it seriously and enforce it if there's a problem. You also will want to look at our mission and values. So this really gives you a sense of how we make decisions about what kind of code we accept. So for instance, we're not really focused on performance as much as readability. So if you read this, it'll explain that if you have a PR that marginally increases the speed of an algorithm, but the problem is it really makes the code much more complicated and difficult to understand. That may not be accepted because we really want readable code more than we want high performance. And so, some of the decisions you'll hear from us will make a lot more sense if you see our mission and values. Also, if you're going to make a contribution, the contributor guide is where to start. So, it tells you right from the beginning, how to fork and how to set up your environment, how to develop your contribution. It tells you a little bit about the review process, etc. It's a very high level, so if you've never used any Git or GitHub in the past, you may want to do some external reading or do some Googling, find something, maybe a friend that can tell you a little bit about the process. However, it's pretty cut and paste, so you probably can get through it pretty quickly. We also, for undergrads out there, maybe looking for submitting a Google Summer of Code project, we have a few mentored projects that we've listed some ideas that we're willing to spend some time mentoring younger students and younger contributors with. There's also a newly started frequently asked questions for new contributors. So, we're starting to get more and more people that haven't contributed open source before or NetworkX, and they have this question about how to get started. I've given you some of that information now, but you can find out more here. And if you have good questions, we'll try to add them and answer them here as well. There's a core developer guide. So once you become a contributor and start working with us more regularly, we may reach out to you, or you may ask us how to become a core contributor or core developer. And then, if we do that, then there's information about what that looks like. You can look at it now, but that's really more about, once you become a core developer, you start having much more responsibilities for helping other people contribute to the project. Okay, that, I think, finishes up that. And, thanks a lot for attending this talk. I hope you'll attend the tutorial and learn more about NetworkX, and I really hope that some of you will be encouraged to become contributors to NetworkX. We're a very friendly community, and there's lots of stuff to still be done, despite the fact that NetworkX is a very mature project that has a lot of features already. One part is that there's just a ton of network science algorithms and graph theory algorithms, but there's also constantly new developments and room for improvement. So thanks a lot, and enjoy the rest of the GraphXD.